Thank you for attending. In this presentation, I'm going to talk about our project, Collective Driving with Shared Perception to Improve Driving Safety. Self-driving cars has attracted a lot of research and industry attention. Many research has been conducted to develop more robust algorithms to make self-driving cars more safe, but many of them only consider driving an individual vehicle. There is no vehicle-to-vehicle communication, specifically shared perception. Perception of an individual vehicle can be occluded by surrounding obstacles, and real-world sensors all have various levels of noise. This can lead to inaccurate perception measurements and unsafe decision of autonomous driving systems. We can extend the sensing range by communicate with other vehicles or infrastructures to potentially improve the safety of self-driving vehicles. In this research, we are interested in verifying the hypothesis that shared perception between autonomous vehicles can improve localization accuracy and driving safety. Our methodology works as follows. Assume each vehicle has absolute pose measurement by the GPS sensor and relative pose measured by camera. We can then form a pose graph where each vertex represents the pose of vehicle and each edge represents a measurement. This pose graph can be optimized using G2 or other pose graph optimizers. We are interested in the following safety metrics, TTC and TRCRI. These two are common metrics to measure the safety of autonomous vehicles. The next diagram shows our methodology in more detail, where the yellow echo vehicle here can see the front vehicle from the camera and form a relative measurement indicates by the red arrow. And similarly, the front vehicle can see other vehicles and gets other relative measurements. All vehicles has GPS sensor, and therefore they can form a pose graph in the bottom left corner. But if we allow information sharing, then each vehicle can not only see from its camera, but can also tell the surrounding vehicles what it sees, if they are within a certain distance. Then we can form a more dense pose graph with lots of redundant measurements, as indicated by the lower right corner. This way, we applied more constraints to our optimization problem and can potentially get a better solution. We conducted our experiments in Sumo and Carla. The difference between these two traffic simulators is mainly in terms of vehicle control and 3D perception capabilities. We have 4 scenarios in our experiments. One is isolated camera settings. Another is collective camera settings, and collective GPS settings, and collective GPS plus camera settings. The result of our experiments shows in this diagram. The first one shows that as the GPS noise increases, vehicles that only rely on GPS becomes worse and worse in terms of localization error. But if adding shared perception from cameras, then localization error has almost no effect. The second diagram indicates that vehicles rely on camera all being affected by perception noise, but with GPS measurement, the error is smallest. The last experiment shows that as the communication radius increases, more objects will be detected for collective perception cases. The conclusion of our experiment is that communication enables the vehicles to see more objects beyond the line of sight, and localization error can be significantly reduced by pose graph optimization of redundant measurements from multiple vehicles. In future work, we are looking to conduct experiments to verify that collective perception can increase driving safety using metrics we discussed before, even at the presence of various noise in the sensors. This is the end of my presentation. Thank you very much for your attention. If you have any questions, I'm happy to answer that in the Q&A sessions.